Our last day of new material. Sorry for the... Yes, we are reviewing next week. I offered to my OChem 1 class, because in OChem 1 I ran out of time. So I was like pounding down the last few reactions right at the end of class. And I said, if you want, we can postpone and do the unit test next week and have no review. And I said that, of course, joking. I wasn't actually going to offer to postpone it. I don't know. I'm sure some of them had some mixed emotions, like, yeah, let's do it. So anyways, you guys don't get that joke. You're going to have your unit tests this week no matter what, because we have much fewer reactions to cover today than I had to cover last night.
I thought you were going to say OChem 2 than OChem 1, and I was like, don't lie to me.
No, it's quite the opposite. Many more reactions in OChem 1. Okay, I made a mistake on this worksheet in the fall, and I didn't correct it. So, we are covering our last two reactions. One is the Michael addition, and one is the Robinson annulation. The Robinson annulation, do you guys know what annulation means? It means ring making, but I'm not quite sure what it is related to. The first time I looked at it, I thought it was related to the word annual, but it's not. It does look like it's related to the word annul, and I don't know if it is. Like maybe annulment is full circle. That sounds like the opposite of full circle, like it sounds like start and end. I don't know. But the Robinson annulation is actually a Michael addition followed by an intramolecular aldol condensation. So Robinson got off easy. He just picked two reactions and put them back to back and named it after himself. Classic dead guy behavior. So first, a Michael addition that is not necessarily credited to Michael because the other name for the Michael addition is conjugate addition. You guys remember the name of this functional group? Our starting material. Don't say ketone. Alpha beta unsaturated carbonyl. Yes. Also called a conjugated carbonyl because it's conjugated with the alkene. So by conjugate addition, we are running a reaction actually with the conjugated alkene. Okay, I think before I show you this, I want to explain some of the interesting chemistry at this position. We have known for a long time, that there is a strong partial positive at the carbonyl oxygen. And quickly, the reason for that is, why is...
Electronegativity of the oxygen.
Perfect. Electronegativity of the oxygen puts a partial positive on the carbon. And we know that we could show a resonance form where those electrons are pulled up to the oxygen. But we don't love resonance forms that put a positive charge on a carbon. Or if we do form that, we look for other ways that electrons could move. And in this case, the conjugated carbonyl can be shown moving from alpha beta towards alpha carbonyl. What the conjugated system tells us that we would not have necessarily guessed otherwise is that there is a partial positive at the beta position as well. And we know there's a partial positive because there is a resonance form where that carbon holds a positive charge. Lily?
Are you missing a methyl group around there?
Sure am. Thank you. I am missing that methyl group. Can we say the same is true about the alpha carbon? Does the alpha carbon also have a partial positive? No, not nearly to the same extent that the beta carbon does, because the alpha carbon in both resonance forms has electrons, has a satisfied octet. So the conjugated carbonyl is electrophilic at two places. It's electrophilic at the carbonyl carbon, but it's also electrophilic at the conjugate position, at the beta carbon. So when we look at reactions that involve this conjugated carbonyl, first, let's consider a reaction with a, do you know what, actually, I know this isn't on your sheet. I know you've only got left, right, and up, not isolated, and then right. I want to start by going down. I want to show you something that you've already seen before. You're going to have to add the down in. If we take a strong nucleophile, like, for instance, an organometallic, and I react a strong nucleophile, that nucleophile will attack at the strongest partial positive, which is at the carbonyl carbon. We know that acyl addition with these strong nucleophiles requires us to have an aqueous workup so that we're not just left with an alkoxide, but we get an alcohol product. This demonstrates, though, that a strong nucleophile, or if you will, a strong magnet, is pulled directly towards that partial positive of the carbonyl carbon. But if I have a weaker nucleophile, perhaps a nucleophile that wouldn't necessarily be able to open the carbonyl carbon, wouldn't be able to do acyl addition, it can attack at the beta position, because attacking the beta position pushes the electrons just like this and creates a resonance stabilized system, the enolate. So to the right, we're going to introduce a moderate nucleophile, a weaker nucleophile. Let's introduce the cuprate. I'm going to show again what this, sorry, I'm going to do this in a different color. I want it to stand out a little bit more. This is methyl cuprate. If you guys remember, the cuprate has two organogroups bonded to copper, and the lithium is acting as a counterbalance for the negative charge. But we addressed back in Unit 3 that cuprates are not the same as Grignards, and they're not the same as organolithiums. They are weaker nucleophiles. They're more moderate. They're not strong. The cuprate is not able to attack the conjugate position. I'm sorry, is not able to attack the carbonyl position. Instead, the cuprate attacks the beta position. Lily, I forgot my methyl again. If you hadn't have caught me earlier, I would have just kept missing it. Did I miss it here? No. Okay, but this is not our final product. Sorry. Because we follow this with an aqueous workup. This is just an enolate. We've been dealing with these the entire unit. That enolate is in resonance, negative on the oxygen, negative on the alpha carbon, and we already know that the reactive form is when the carbon holds the negative charge. So after that first step, I just form an enolate. So I would like someone to reason. Why does a weak nucleophile attack the beta position more readily than it attacks the carbonyl position. What about the beta position? What about the intermediate formed means that a weaker nucleophile is able to actually attack there? Indigo? I don't think there's a bond to hydrogen that's lost.
On the carbon? I guess when it attacks.
So it went from CH2 to CH2. If you'd like to see the mechanism, it will actually look quite similar to this. So here's our nucleophile. And the nucleophile attacks at the beta position, pushing the pi bonds up to the oxygen. Or, because we can show any resonance form at any time, we could have stopped with the negative charge on the carbon. But of course, we know it's more stable when it's on the oxygen. Anybody else? Milena?
The resonance that you previously put a positive charge on the beta position, so it is more often Lewis acid effect.
More than the carbonyl carbon?
Not necessarily, I'm not sure if more, but it's probably a little bit
More
more accessible.
accessible? Lily?
Yeah, that's great.
Was
I was just gonna say maybe something about the partial positive and partial negative, but I don't know.
So maybe there's a distinction between the partial positives at the two positions. Maybe it's accessibility, steric strain, although I think we can argue I could make this an aldehyde and this could have more carbons, but we'll see a similar effect. A weaker nucleophile does conjugate addition. And then, sorry, I didn't show the final product. This is what we isolate after that acid workup. A weaker nucleophile does conjugate addition. A strong nucleophile does acyl addition. And again, here was that intermediate formed after acyl addition. Can you tell me a distinction between the intermediates formed from acyl addition and conjugate addition? What's different?
That forms an OH group. That's carbonyl.
Okay, you're right, but that's the final product. The final product does form an alcohol, as acyl addition does. This forms a ketone or a carbonyl as enolates do. But the intermediates, what's different about the intermediates versus between acyl addition and conjugate addition? Max?
For conjugate, there's different resonance forms of it.
And acyl addition?
There's none.
No resonance. Resonance is the key there. Resonance has what effect on reactive intermediates? More resonance is more stable. Resonance is a stabilizing force. So why is it that a weaker nucleophile attacks by conjugate addition? It's easier to form that intermediate. That intermediate is lower energy and more stable. It's harder to form an intermediate that has no resonance. That's the key here. No resonance would take more energy to form. Has resonance, easier to form. Good? Strong nucleophiles, acyl addition. They are all right without resonance. They have the energy needed to get over that activation barrier. Or maybe I should say rather, the activation barrier to them is smaller. Weak nucleophiles will traverse over the lowest energy activation barrier. They go for the resonance stabilized intermediate. We also have different names for these. This is called 1,2 addition. I add a group to the carbon and I add a hydrogen to the oxygen, so I add 1,2. This is referred to as 1,4 addition. Conjugate addition is 1,4 addition. The problem is it looks like I've added something to alpha and something to beta. I added a new group to beta. I added a hydrogen to alpha, which looks like 1,2. But because we form this enolate intermediate, we can, in theory, say that the oxygen sometimes takes that hydrogen and then tautomerizes between enol and carbonyl. And so we do 1,4 addition, but it just tautomerizes into a different isomer. But they do refer to it sometimes as 1,2 versus 1,4, acyl addition versus conjugate addition. Another weak nucleophile that we can take advantage of, an enolate. Enolates themselves are not super strong nucleophiles because enolates themselves are sometimes the negative charge is on carbon, sometimes it's on oxygen. So if I introduce an enolate, and there's a few ways that I could show this over the reaction arrow. Maybe I can do this in different colors to illustrate the different ways I can introduce it. One, I could just introduce an enolate. This, of course, would still need to go through an aqueous workup because there is no source of hydrogen for the protonation step. I have a nucleophile, alpha, which is actually going to attack my beta position and become beta to the alpha, but beta was already alpha to something else. So my final product is what functional group? It can be hard to spot the pattern unless you know what functional group to look for. So I had you guys name this functional group at the start of this unit. What?
At the beginning of the semester?
Unit.
Oh.
A something dicarbonyl.
Oh. Now can you go?
A shared beta dicarbonyl. If an enolate does conjugate addition, then alpha is attacking beta for something that is already beta to something else. And now both carbonyls share that beta position. This is my tip to you. When you are predicting the products of Michael addition, look for the shared beta dicarbonyl. Both carbonyls should have a shared beta position. The alpha of one carbonyl is attacking the beta of another carbonyl. All right. So we have conjugate addition, which is just generic any nucleophile. Specifically, when that reagent is an enolate, conjugate addition is called Michael addition. There are some other ways that I could introduce these reagents. So alternatively, I'm sorry that this is not really near to it. And Lily, let me know if you can't see you guys all in the back, let me know if it's hard to read the orange. I've introduced that as literally just an enolate. I didn't even show the counter ion. I'm assuming a spectator ion is balancing it. But maybe I don't want to show the enolate itself. Maybe I want to show how I will form the enolate. So I could take a carbonyl with LDA, and I could write that as step 1. Because a carbonyl with LDA will completely enolize. It will turn 100% into my enolate. So these are the same. Would you agree? It's just showing how this combination is going to appear in the reaction, or how this reactant is going to be formed. They are identical to each other. Okay. This is where I messed up in my worksheet. When you have a shared beta dicarbonyl, if the positions are correct, if the hydrogens are available, these can react with themselves through an intramolecular aldol condensation. And this product that I've shown can react through an intramolecular aldol condensation, which means the Michael addition needs to have some more limitations. For instance, it needs to not have available hydrogens on the exteriors of those carbonyls, away from their shared beta position. And that's because if I do create something like this, especially in the way that it's already negatively charged before the acid workup, the enolates can reform. Enolates can do acid-base chemistry with each other. And if I form an enolate where one of these exterior positions of the carbonyls is negatively charged, it now runs an intramolecular reaction. Alpha will attack a carbonyl, which will become a new beta, 3, 4, 5, 6. By alpha attacking this beta, it forms a 6-membered ring. One part of the molecule attacks another part of the molecule. Oops. So here's alpha, which has now formed a new beta. Notice also that the beta had an unlabeled methyl group, so beta still has that unlabeled methyl group. And that is the Robinson annulation. Sorry, I didn't indicate that this also requires an enolate in that step, because we're just doing Michael addition, but the product that forms there then just does an intramolecular aldol condensation. Together, the Robinson ring-making reaction. Elena?
Which part of this is the Michael addition?
This is the Michael addition, although I did skip over how it will tautomerize from this type of enol into this type of enol. The important thing is that if it can form an enol like this, or an enolate, then it will react with itself. In the OChem 2 lab, we used to have an experiment where you would take a conjugated carbonyl and an enolate, I don't even know if I have the old procedures for it. And you would create an enolate, react it with the conjugated carbonyl, and run Robinson annulation. And it happens just about as fast as that last reaction happened this week. You guys saw how quick that last reaction was? You put it on the table, on the stir plate, stir it for a few minutes, and then it's done. It happens just about that quick. These reactions really don't take long to run. Let me show you what it looks like. Questions on this while I get this pulled up? Mapping your carbons becomes pretty important. And being able to recognize your functional groups, predict patterns between these groups. I think I'll draw this one on the board as well. Oh, yeah, that makes it really hard to see. Oh, man, okay. What starting material is that, by the way? Oh, yeah, you're right. Ethyl acetoacetate. And we'll turn ethyl acetoacetate into a nucleophile by introducing sodium hydroxide, which means that, as an enolate, it can attack the beta position of this trans chalcone. You guys made a chalcone, didn't you? Oh. Oh man, this became so much easier than I thought to do this. A derivative, you're right, but it is a trans chalcone at its fundamentalist. Oh, okay, yeah. So to the future students of watching this, if that's anybody, I don't know why I never did this. I'm just going to modify whatever trans chalcone you guys made in lab. Then you just mix in ethyl acetoacetate with base and run a Robinson annulation with your product. So we form a nucleophile. That nucleophile attacks the beta position and creates this shared beta dicarbonyl. But because I still have that catalytic amount of base, it continues to react from this alpha position. Notice how it has actually swapped which alpha is acting as a nucleophile across the two reactions. And it attacks the carbonyl on the ring. Leaves us with a 6-membered ring. Couple of phenyl groups. Intramolecular aldol. Incredible. And it happens in seconds. It is not a long reaction. I took this one out because I couldn't make space for both. I did not have the foresight to see that they were really just sequential. Take your product and react it further. Dang it. Well, anyways, here's some examples of that resonance. The enolate nucleophile is distributed across 3 resonance forms. As it does conjugate addition, it forms an enolate intermediate, which is why it's able to do conjugate addition. The enolate intermediate gets protonated and gives us our shared beta dicarbonyl. And then the base that has been reformed creates a new nucleophile. Elliot brought up a good point, and actually this is something I'd want to point out even more, this position is actually the most acidic in the molecule. It is distributed in resonance across 2 oxygens, and it's tertiary, so it's the most acidic hydrogen in the structure. So in order for this reaction to run, we're betting on the fact that deprotonating this position can happen, even if it's less likely or less energetically favorable. It can happen, and when it does, it runs the Robinson annulation. And then, of course, this here is just the mechanism for intramolecular aldol condensation. That's a mechanism that you guys know. That's a mechanism that I will have you potentially show this weekend on your unit test, or the Claisen condensation. Milena.
So the second part of the Robinson annulation, you said it was an aldol condensation, right?
Yes, Robinson annulation is Michael addition plus intramolecular aldol condensation. Okay. The end.
Really?
That's all our reactions. So I would like you guys to solve these synthesis problems. Think about what functional groups you have, what functional groups you need. Very fun. If you would like an additional activity, what I would encourage you to do to challenge yourself is to create your own multi-step synthesis that involves reactions from every unit, maybe every section. Does not have to be sequential. It doesn't have to be that you start with aromatic reactions and end with condensation reactions, but to take one reaction from each unit or one reaction from each section and try to string them together into a synthesis. They're all quite related, right? Back in the reactions with aromatics, we showed acylation with acid chlorides. Well, you know how to make acid chlorides from our time in Unit 4, working with carboxylic acids. And you know how that can be related to aldehydes, or not aldehydes, sorry, carboxylic acids, which are related to alcohols from Unit 3. And also, if you make an acyl group, then you can set up to do some sort of condensation reaction. They're all connected, and I don't want you to believe that they're not. So a challenge to you would be to create a multi-step synthesis that uses at least 5 reactions, one from each unit. I will not put the best one on the final.
That's so mean, because then I could come up with it.
Because then one of you is going to have way too easy of a time on the final.
That's the
If you're not crying when you leave my final, I'm not doing something right.
That's so mean, John.
That is really mean. I don't mean that. I've only had a handful of students cry so far.
This is 1 and this is 2.
Correct. Yeah, you'll notice actually with the second one, you have to come up with starting material to make the product shown. Mm-hmm. Very fun. Very clever. Okay, the time is yours. Let me answer questions as they come up. Those are all the reactions. We can talk about amines if you want to. Amines is the next chapter.
Wait, what? Will that be on the final?
It will be if we talk about it.
Oh, no.
I can publish an active. You guys still have a week left of class.
No.
You want to do amines?
I got other classes I still got to do stuff for, too.
Well, you're saying that's it. Like, I have the rest of the textbook, you know? We just stopped early because that's usually the time we have.
Great, yeah, pay me quiet.
Okay, let me write out instructions a little bit more clearly for that challenge, but in the meantime, work on these synthesis problems. Oh, actually, I just realized Unit 1 was all review. So at some point in there, you'd have to work in an OChem 1 reaction. But do you remember how many of the OChem 1 reactions we reviewed at the beginning came back later on? Almost all of them. Maybe the only ones that didn't were like Diels-Alder. But actually, I could wrap the Diels-Alder back in.
Oh.
That's a dienophile. That reacts with the Diels-Alder.
You can make a ring by that.
Well, yeah, you can make a ring by a lot of things, but you're right.
But yeah, I'm just saying that's a good thing to remember.
Yeah. For what?
What if I need to make a ring?
Yeah, if you do need to make a ring, good idea. Go to the cyclo addition reaction. That's a good idea. Actually, OChem 1 lab upstairs right now is doing Diels-Alder as we speak. No one speaks after that.
Literally does not know how to put their stuff back. Oh yeah. I swear.
It's not OChem 1. It's the Gen Chem labs.
They are in that lab too?
Oh, yeah.
Oh.
There's several 1115 and 1215 labs in there.
Okay, just kidding.
Several. There's only 6 organic labs this semester, but there are like
Like 1 and 2. Oh yeah.
yeah, but there are like 40 general chemistry labs this semester. You guys are all right if I erase this?
Yeah.
You got it?
Just go back and look at it.
Good idea.
You didn't write it down. No, I did. There's just other bits and pieces that I have to I tried multi-step synthesis, I just blank. I'm like, I don't know how to get there. She's like, that looks neat. I showed you how to do it.
Well done. Round of applause to whoever wrote that synthesis.
You guys did a real good job because I can't do it.
Spot your functional groups. Look for what changes you're seeing. How can you work forward and backwards?
What the heck happened here? Where does... Oh, I see.
Yeah, going forward.
Oh. Isn't there like some weird thing that like I can just close a ring? I can just make a ring like not like that, but like there's something that we learned that it was like do this and then it closes.
Like the intramolecular aldol or the
I don't know.
the Deichmann intramolecular Claisen?
Wait, this reaction we did, that was the intermolecular. Who was this guy?
This is the intramolecular aldol,
Okay,
but this combination is Robinson annulation.
this whole thing is it?
Michael addition, intramolecular aldol, Robinson.
Okay,
Because as I said on the sheet, this is not isolated. You won't be able to get this product.
okay.
I understand. I think I see how I should have maybe done the. Never mind.
Wait, how do we
Yeah.
feel about
Yeah.
how do we feel about this? Not good.
What? No, don't let me stop you.
I don't know, your face was like
It looks like a structure, yeah. You're doing great.
thank you so much. Wow.
Okay, that clearly didn't come across right.
On a roll, John.
He's like, yeah, I've unfortunately had to watch your lectures.
No, I didn't say that. I said, Hatta Anna, like literally the same for me. About me. My goodness.
So is it technically, it's possible in this many steps, but I can choose as many steps as I want to?
Yeah, I guess, I would say, see if you can do it in that many steps.
I already know I can.
Okay. Gave up before she even started.
Does it like because we have the shared data carbonyl?
Well, you tried to use the stuff from above, so that works.
Look backwards.
I didn't.
Or like have that guy here.
Yeah.
Want that form?
I have no idea.
What is this called again? It starts with an E.
Sorry.
Oh,
Enolate,
enolate.
which is enol,
That doesn't make it.
but negatively charged. Enolate.
What?
How do you end up with two carbonyls when the whole point is that the two react together? Like,
Hmm.
or are we regenerating this?
That's the final product.
Right.
Hmm.
Yeah, that's what I'm confused about.
Mm-hmm.
Because in the one given, right, like
Get
you
your
make
hair done.
an intermediate with two, and then they react together.
Yeah,
So are we
yeah. Oh,
expected to
actually,
make like
maybe that.
something that doesn't have one, and then like regenerate one? Is that what?
I don't know. I was like, did I do
Okay.
what?
I just want to make sure I'm understanding like this correct. So
Well,
we're
I
supposed to
just-
use an
I
older
didn't,
reaction that makes
like,
carbonyls
Dye it and just
off of
dye
like
it.
this would be the Robinson
I'm
product,
right here.
Ah.
and then we
I don't really know how to respond to this.
regenerate
honestly.
carbonyl.
Yeah.
Okay,
I was like, I mean,
Yep.
that's helpful. Thank you.
Good. You bet.
but I put this
Yes.
I was just thinking about what we did last class.
Good work.
But I'm thinking about the reagents now, so.
You're on a great track. I'm not gonna lie. That one stumped me so much that I pulled up the fall recording to see what I had said. In the fall, we actually didn't have this much time. We ran out of time. I had to just fill out this worksheet online.
We should have asked more questions so we didn't.
Peyton tried. She tried talking my ear off. Right? You literally admitted to saying, I try to get you to talk as much as I can so we don't have to. I don't know. What was your goal? So we don't have as much time to learn?
No, it's just, you know, like when you're not locked in and you're just like, I hope he just keeps talking about stuff. Like, I don't know. I don't really want to do it today.
This is a great product for this synthesis,
Huh?
but it shouldn't be here.
What?
It won't be at this stage. So what you've what you're saying is, let me make an enolate,
I can't hear.
attack this
I don't
position,
know what's happening.
and then I'll have this
I literally can't hear.
attack the carbonyl back. But we said that would form a conjugated carbonyl,
I think you used
Not
all words for it.
a conjugated carbonyl. So if this is not a conjugated carbonyl, it couldn't be Robinson annulation.
Okay. So I'm seeing, this is
Well,
the
I-
shared beta
to be fair,
carbonyl.
like,
Yes, yes.
That's all I figured out. And I've found there's 5 more carbons.
Great, love that.
He was like, I just wanted to be included.
Another thing I might point out is the structural relationship between these two ketones.
Oh, sorry.
Like this alpha?
Could you
Shared
like
alpha?
a shared alpha? That's one way to say it. We did have a name though for carbonyls that share an alpha. If you name one of them as the primary, then the other is beta, a beta keto carbonyl.
Oh.
And we
All one step, right? Or this isn't. It's not a whole. Is it a whole reaction?
no, you're adding reagents at each step.
No, I'm saying like. Oh, but
It's
these
one
two
and two.
separate
Yeah.
things.
Yeah,
Okay. I
there.
was like, guys. I'm
No,
not
you're right.
doing
The
this.
bottom one you have to solve for the starting material.
Okay, that's fine. And so it can just be either.
You like what I've drawn so far?
I like what you've drawn and scribbled out. Yeah.
Was it correct?
Well, maybe, yeah. I mean, it's hard to say. Because LDA followed by H+, I'm not sure what it tells me.
Well, it's turning the this into an enol.
But then why would you put H+? That would destroy it.
Well, instead on the board you said LDA and H+.
You're right. That was actually with another reagent already provided. So it was this with LDA
Okay, and then that makes the enol. And then you
reacts
add
with this.
Okay.
Yeah, yeah. Think about what functional groups you have. Think about ways we've formed those functional groups. Just died? Sorry, this is me nitpicking. What I was looking at with that face I made earlier was your alkene. It disappeared. You had a funky looking alkene that had it had the two groups coming off of it like that.
The one that's erased.
Oh, you erased it. Which is just like, you know.
I'm like, does that even happen? Oh yeah, okay.
So it was just this group not being drawn in the right orientation.
Okay.
That's all.
Okay. So that could be a product you're telling me, or that could be part of it?
Yeah. I won't tell you that.
Am I on the right track? Do you like where I'm going with this?
Mm-hmm.
Maybe I was just from last class. I'm just gonna sit here
So I think you're getting all of the carbons that you want, right?
I think so.
But then you'll have to
Connect them?
connect them.
That's like what I'm planning. I think.
I'd love to see it. I'm not sure how you're going to connect them.
Oh. Is there a way that I can have like this on a ring without the double bond? Say there's like something bond in here and something bond in here, and I eliminate them. Is that a thing? Oh.
Oh,
I eliminate
to like cleave.
something to then create the double bond that's right there. Is that a thing?
Oh, yeah. You're asking if you can run just a typical elimination reaction.
I don't know. Can I do something? Like, is that allowed?
You can,
Great.
if you want to. I think that's what you're saying.
Yeah.
Hydrogen and bromine leave,
Yeah.
just like OCHEM 1.
Yeah.
Yep.
Oh, great. I did something. I got one thing. I have just an eraser. Mine's ready.
I do not. Oh, I have this. Yeah.
Thank you, John.
Mm-hmm.
Why do you call this a shared beta keto? Because isn't this an alpha carbon?
Is it both? Shared beta.
That guy, yeah.
Not share. I didn't call it that.
Oh, we
I
call
called.
it that.
I called.
Okay.
I called that.
Okay.
This is a beta keto carbonyl. So just get rid of shared. It's a beta keto carbonyl. Here's a carbonyl.
Okay.
Alpha, beta.
Oh,
Yeah.
oh.
There's a carbonyl on beta.
I see. Okay, thank you.
Mm-hmm. That's a really hard one. I'm honestly not even sure how I came up with it. Yeah.
I have two questions.
Tell me.
The overarching question is, does this work? And then the second one is like, if you would have this extra methyl and you react L-beta here and create that, right? Would it then just like add the little methyl? Does that work?
Okay. So this and this come together to form this.
Isn't that what's happening here? Is that they react together? Oh, that's
Yes.
an aldehyde.
Okay, good.
Sorry.
Although one thing is we need a base to facilitate the reaction.
Could you use like an AOH for this one?
Sure, sure. But because we've got this crossed aldol, our best way is to use complete enolization. So what you might want to do is turn one of these into the nucleophile first, and then introduce the other one.
So would you use like,
Which of these should be the nucleophile? Can you say?
I feel like the aldehyde? Because it's more reactive, right? Or-
Well, regardless of reactivity, it actually is determined by our structure.
Oh, because the beta. Hold on.
Mm-hmm. Creating a ring.
Would you want it to be the?
Maybe.
Would you want it to be the ketone? Because the beta attacks alpha, or is it alpha attacks beta or beta attacks alpha?
Good question. Let's consider this enolate. Here's alpha, which is actually nucleophilic. So alpha attacks beta.
Okay.
And here's alpha, right? Which came from which group?
Ketone.
The ketone.
So you'd want that one to be the nucleophile?
That's right. So I would say first LDA, which means that this with LDA becomes just an enolate. Second, the aldehyde.
So you'd just say 1, 2?
Yep, exactly.
Okay. Is there like a reason that like this would be 1, 2, but then you wouldn't write just like LDA and then the next step? Like what separates?
It depends on what you think that you need for this synthesis.
Okay.
I've given some weird constraints where I'm saying do it in this many steps. But if you're not limited to that constraint, then you can take it further.
I just wanted to check. And then, so is that, am I insane for thinking that this with
I
this would
think
work with create that?
you're missing your double bond here, right? The between C and O, the carbonyl double bond.
But would that double bond? Yes. Yes.
Conjugated carbonyl.
Because then that one would work.
No, this does work then, because we have our conjugate.
yes,
Oh,
okay.
I see what you mean, yeah. All right, so if our nucleophile attacks here, then I get this carbon chain all added together.
Sorry, that's my work.
It's okay. And then this carbon can become deprotonated and act as a nucleophile to that. The problem is what I see happening, actually, yeah, let me just label your atoms a little bit. Let's call this alpha and beta. In the product, here's beta, and here's that alpha that just attacked.
Wouldn't it be the aldehyde thing? Or not the aldehyde, the carbonyl?
Well, this alpha is going to attack this position,
Yes.
right? And this position, relative to the carbonyl,
Okay.
is
I see what
here.
you're saying.
And then I just formed this group. Beta already had one methyl, but not two.
Oh, well, because this one has the extra.
It has one methyl, yeah.
Mm-hmm.
So it's going to continue having just one methyl. But alpha is now going to bond to it. It's not a new methyl group, but it is a new bond.
Okay.
And then off of alpha, I've got this carbon. You see it?
Mm-hmm.
And off of that carbon, I have a methyl.
So okay, then we just have to work a little bit.
Okay.
And then the Robinson annulation leaves us with a new double bond.
Okay.
Unfortunately, it doesn't give us a dicarbonyl, right? And it has our methyl groups in the wrong spot.
Okay.
But maybe this gives you some clarity about what to do in this first step, because you're seeing that even if I do form a ring, I don't form it with the right number of methyl groups where I want it. So how far back can you go to get the two methyl groups there?
Can I get a vibe check on this?
Sure. So you're saying take acetone, turn it into a nucleophile, first LDA, then add acetone.
Yes. So then we have our, because we're trying to get the beta keto carbonyl.
Mm-hmm. So first of all, if I want to use complete enolization, that's usually because I want to react it through a crossed reaction. So a different carbonyl. Why would you? Yeah, so then I could just say instead, take this and react it with NaOH.
I can just change the two equivalences? Yeah, is that cool? Sorry.
Yeah, I'm always struggling with this. This is the part that's hard for me to get across. And I want to see if I can get it across well. If I have one equivalence, or like it assumes that it's one equivalence, but I want this reagent to react with itself, would I actually need to double the equivalences? Not really. Like it's there. It's not like I have just one molecule. I've got this reagent. And this reagent, in the presence of sodium hydroxide, will react with itself through an aldol condensation.
So could I just do NaOH instead of what I did?
Correct. That's what I would say. If you're looking to do just a regular reaction, you don't. If you're looking to do a classic aldol condensation, you don't have to use the LDA. If you're looking to do a crossed reaction, LDA is useful.
So is this like a good first step?
Yes, but aldol condensation yields what kind of product? What functional group?
But it like feels right.
NOH.
On the top one?
Okay, your options include beta hydroxycarbonyl, alpha beta unsaturated carbonyl, beta keto carbonyl, shared beta carbonyl. Aldol condensation does not make a shared beta carbonyl.
Conjugated aldehyde.
Right.
I literally get everything done. I think all what I think I need. And then I take good one.
If you wanted to make what you had, Katie, what type of group do you have? A beta keto carbonyl, which is similar to the Claisen condensation. The Claisen condensation is the one that gives us a beta keto carbonyl. And the Claisen condensation requires an ester to be present because the ester has a leaving group that can leave. Can I say that louder?
Oh, and then that ends up as the beta carbon. No.
The ester carbon,
Beta carbonyl, right?
yeah, the ester carbon becomes the beta carbon.
That's what that is technically.
Okay, Ella said the quiet part for me. Say it louder.
What, that
That,
is the beta carbonyl.
which is made by
That.
that. That is that.
I don't know what reactions.
Well, there's not a good name for it. I just called it crossed.
That.
Because if it's aldol, it's combinations of aldehydes and ketones. If it's Claisen, it's combinations of esters. But what happens when you combine aldehydes and esters, or ketones and esters?
I just don't get how it ends up as a ring.
Something intramolecular will have to happen.
Oh no, I get what you're saying, because it's gonna look like that, and then something intermolecular is gonna happen. It's gonna like attack itself.
Uh-huh.
And then it's gonna end up as a ring.
Yeah.
The gears are trying to turn. So that is, oh, but then Does this?
Count them.
But like.
And if you want to move on to the next one too, you can. Oh, you guys did. Okay. This does work. I would have liked to see a reaction from this unit.
You didn't say that.
You're right. That's why I said I would have liked to see it. I'm also not giving you a grade on this.
I know.
She's doing the second synthesis.
Oh, I know. I just did.
This is close, but it needs to be first, second. And the cuprate has 2 equivalences of the carbon. So we could put a parentheses around it and say 2. Yeah, like that. I wouldn't put the Li next to it either. I would make it clear that the carbon is bonded to the copper. So yeah, this works, and I don't think you can erase, can you?
Yes, I can.
I would draw that parentheses through the bond going to copper.
Okay.
Because it's that bond to copper that's happening twice. Yeah? But yeah, this is great. And
That's where we differed.
this doesn't work.
Added it like that. Well, I feel like I'm missing a step.
You are missing something. But this wouldn't do anything.
It wouldn't add to there?
These aren't reactive to each other. This is not nucleophilic. In fact, you're actually trying to show it being electrophilic. And this is highly electrophilic, but it's not nucleophilic. So you'll have to figure out what this functional group is and how we make it.
Right?
Oh, 'cause
Right.
it was an ester and they joined. Okay.
This is on the right track, but it alone is not reactive enough. So you'll need something to improve the reactivity. I've got some hints on the board, by the way. I didn't tell you they were hints, but now I am.
I still don't.
I know it's a really challenging one. This will not be on the final.
Thank you.
Okay. So I did come up with the ester. I was really proud of it. So you might need an ester, and I was like, yes.
Good.
But can you use like if you keep another ester on the other side, could you get this to then use this to make a ring?
Oh, maybe. Yeah. So you got to be careful about your ester. This is not. This is an ester on the right, but that's an ether on the left.
Why is it?
You have an sp3 hybridized carbon between the carbonyl and the oxygen. And here, right? That carbon between them. Were you relying on that carbon?
I think you would need that carbon though, right? Because otherwise you wouldn't have enough to make your ring.
I see. I also don't see where the 2 methyl groups will come from.
That was gonna be a next step problem.
So I think maybe you need your ester somewhere else in the synthesis. But you should be proud that you thought of an ester being in there.
What do you mean by like somewhere else in the synthesis?
Like maybe instead of early on as step 1, maybe it shows up somewhere
Oh,
else.
you mean like the ester in general?
Yeah.
Just gonna write it out.
What is this? Oh, ET. Sorry. You've got them mixed. Yep. So actually, if you just erase the 1 and 2, brilliant.
John, I don't know what's going on.
Where are you at? Okay. Yeah, you're.
I don't know. This is literally what happens when I do multi-step synthesis. I just look at it.
Well, let's brainstorm. That's one of the rules about synthesis, right? Brainstorming.
So I get that in order to get the beta carbonyl you have to have the ester and then
Because it's a Robinson.
I don't know what. So I don't know what reaction does that. Is that what it is?
You say you got it?
Almost, I think.
Am I getting close?
Mm-hmm.
I just need to
You
remember
are getting
how to
close.
do- how to make this
from a double bond.
You're right. In fact,
Remember how-
I think we have an example on it from yesterday's reaction. Kind of. Deichmann, though, has two esters by nature, and that would leave an ester in the product, and we don't have an ester in the product. So it's going to be Deichmann-esque. Spell that. Deichmann-esque.
What does S mean?
Like vibes, yeah. Deichmann-ish, Deichmann-esque. Like a Deichmann. That's, you guys use that? Esque?
Yeah.
Can you use it in a sentence other than Deichmann-esque? That's very,
But we don't want an ester.
I don't know. I really couldn't tell you.
It's like hard to think on the top of your head, but in like a sentence, it's just so.
I have a folder in my on my computer that's called CV-esque because they're like things that I could put on a CV, like my academic records, the things that I do for the school, the ACS conference I put in the folder CV-esque because although I'm maybe not writing it explicitly on a CV, there are things that kind of go on a CV. Beautiful. Captures the essence of. Essence-esque, if you will.
I can't find anything to make that.
I have a question. Maybe I should have clarified this on Tuesday.
Is that all you added?
Yeah.
No. Well, first, you would want to show a 1-2 there.
Because I know this is, I feel like, essentially what we're looking for to go backwards, right?
Yes, you're exactly right.
But what is the retro? Because
Oh, it just means this comes from this.
it just spontaneously?
Oh, we didn't provide the reagents.
Yes.
You would need a base.
Oh, just would any base work?
Well, you got to be careful anytime you have an ester. The base should match the ester so that it doesn't hydrolyze or transesterify.
Okay. Would something simple like MEOH work?
Well, MEOH is not a great base. How could you make MEOH a better base? No, not quite.
I said MaNOH or something like that.
Oh, ME, methyl.
Yeah.
Katie, how do you make it a better base? Basify it. Yeah, karyo, charge, atom, resonance, induction, orbital. Charge, make it more negative. More negative is more basic. How do you make methanol more negative?
That other people are just not getting it. I'm not.
Meth oxide. Instead of MEOH, MEO minus.
Check out this blank paper. Unbelievable.
Great. This, interesting. I don't know how well the Wittig reaction works with carbonyls on it. Because Wittigs are reactive with carbonyls, so I would be worried about the two molecules just reacting with each other, right? So there's another way. And I would suggest doing something to get this group on before doing this. Because you'll notice that this is a multi-conjugated carbonyl, right? So how can we control that it attacks here over here? Yeah. But what I mean is do that before
Yeah.
having this multi-conjugated thing.
Oh, okay, yeah.
You're on the right track.
Wait, are you just trying to figure out the last step of the first one?
Yeah.
Okay, that's where
I still haven't done it.
Making music with my markers. Have you brainstormed anything else?
Because this is like what we were doing last week. So
No.
this is essentially like what we wanted to close the ring with, right?
Well, because all I'm thinking about is the fact that I need to get the beta car or what the beta Carbonyl.
You said strong base. You have a strong base.
You're just focused on that.
I know, but I don't know how
But there is another descriptor in this molecule. It has a shared beta dicarbonyl structure as well. This position is a shared beta dicarbonyl. And we can get that by what type of reaction?
Dude, my hair was like actually going wild today.
Ella, for that one, we need a conjugated carbonyl that allows us to do Michael addition.
I don't even know what conjugated carbonyl is.
This is a conjugated carbonyl. Keep reviewing them, I'm telling you guys. I have not seen another organic professor that names these functional groups in the same way. I actually invented this one, the shared beta dicarbonyl, so that you could recognize the patterns. So I mean it when I say get familiar with those groups, because when you see those patterns, it just becomes super easy.
Would it dishearten you if when you died, somebody named it the flood reaction?
I would roll over in my grave. I was gonna say I'd kill myself, but I'm dead.
I'm already dead.
I'd rise from the dead just to kill myself. No. I would roll in my grave. I actually won't have a grave.
How do you know?
Probably be cremated.
How do we know?
My ashes will.
Fly out from the ground. How do we know that the shared beta dicarbonyl needs a conjugated carbonyl?
That's how we make a shared beta dicarbonyl. So in the reaction we saw earlier today, ooh, look at that, a shared beta dicarbonyl is made by a conjugated carbonyl
Okay, I need to write that.
and an enolate. Now we know. I think,
This, make that.
yeah.
That's the correct placement.
Really?
Well, this carbon should have the dimethyl group.
2? What I have as labeled it says 2?
Yeah.
Okay. Alright, because
It's okay.
I thought, alright, how do we know that this one's going to attack that one?
Again, there's multiple possibilities.
Okay.
This could attack here, that makes a four-membered ring. This could attack here, that makes a four-membered ring. This attacking
right,
here
okay, 'cause it's
is
stacks, right.
forms the most stable ring size.
Okay, and then, because yeah, it's the middle carbon between the two. Okay.
Yep.
These are
Oh yeah, so
hard to
yeah,
visualize.
Yep.
I guess I didn't listen, but the alpha carbon here could also react with that. Why does this one take priority? Is it because it's the terminal alpha carbon?
It's more so because of the ring size. So if this alpha carbon does form an enolate and attack,
More steric strain, right?
it forms a four-membered ring. 1 attacks 2, 3, 4, and then I've got a four-membered ring. So less sterics, actually more angle strain. Sterics is just like having a big group.
Okay, I mixed up the strains then. So
I
it's
said
angle
stacks, but yeah, I bucketed in my head as shapes.
strains. Yeah.
And it would happen either direction. Either of those interior alpha carbons would give a four-membered ring, which would not be great.
Would this work?
Oh my gosh.
No, but you're very close.
Okay.
Because this will take this hydrogen and make this a nucleophile
Oh, okay.
to attack this. But I want this to attack here. So if you just erase 1 and 2, perfect.
Oh, okay, okay, yeah.
Because again, another way of saying LDA and this compound is this compound as a nucleophile.
So in this case, we would be mixing these two together before exposing it to this?
Exactly.
Okay.
Exactly. Although we're just not showing what it forms when we do. Okay, good work. And this is good. Let's have this have an aqueous workup after it.
Oh, okay, yes.
1 and 2 for the aqueous workup. Oh, Elliot, where you wrote eth oxide?
Yeah.
Oh, yeah, your ester is ethyl. That's good. Hi, Lily.
I'm wondering why with this we didn't add both of those.
Yeah, that's a good question. Why does the cuprate only add 1 equivalence?
Like, could I have 4 and it would only add 1?
No, you can't have 4. So copper is a transition metal, and it obeys certain rules. We're actually dealing with copper 1, so that means it is in a 1+ oxidation state. When copper bonds to an organic compound, when it bonds to a carbon, the carbon owns the electrons. So this is essentially like bringing R- to copper 1, neutral. R- 2 times to copper 1 leaves us with a -1 charge, which is why we write out lithium. Lithium balances that charge on the copper. Can the copper coordinate more? Maybe. Copper 2 definitely coordinates 4 groups. Copper 1, I don't know that copper 1 will coordinate 2 groups. After one of these groups leaves and does some attack, well, the lithium is actually there to balance whatever charge it puts onto the other structure and leaves us with that neutral organocuprate. But this is not as reactive, right? It doesn't have any charge pushing it. Okay. Yes.
I can see it. It's in my sights. I see that this is like 1, 2, 3, and that's where that group came from.
Good.
So I need to get this. I just need to get this to attach right here. But I can't figure out how to do that. Because
Do you have this carbon yet?
Isn't it? It's this one.
Yes, you're right.
Yeah. I
Good.
have it. I was numbering that way so I could see. Yeah, so I know that this is gonna have to be the ester.
I thought you just said that this was from here.
Well, oh yeah.
Oh, and you're saying that it's that carbonyl.
Yeah.
I guess because it's symmetry, it doesn't matter which
Well,
side you
that's
say.
technically 1, 2, 3, 4,
Love it.
and then yeah, 1, 2, 3, 4.
Well, remember on Tuesday, we said if you want to retrosynthesize something like this, label your alpha and beta, which in this case would be alpha and beta, and separate them, because that is the thing you want to make going forward.
Oh, because we're saying then. So, okay. So that means, because we know this is what we're adding, so we did this, so I don't need to label that part.
Sure.
And then, so that's alpha and that's beta now. And we want beta to be on there because we have everything else besides these 2 carbons.
Yeah.
So then
So let's break alpha beta.
so it would be like that. That
Yeah.
would be there.
Yep.
But then
And you said you know that this has to be.
an ester.
Great. So let's draw that.
Which like I had it here.
It wasn't though.
Oh, you're very close. But your methyl groups are in the wrong spot.
Yeah, I was looking at that 'cause I was like, the alpha, that's direct, like that would be like pink, pink, or
If you map
or
these
pink, pink
if you map these carbons,
differently.
you're gonna get this, but with the methyl groups in a different spot.
So does this work then?
Because that's what I put initially, and then you were like, what are you doing?
Well, ketone and ketone with a strong base, aldol condensation, which gives
So NaOH?
any base, it's going to give you this. If you want to get a beta keto, you need a carbonyl with an ester. If you have 2 ketones, you're not going to get a beta keto group. If you want to get a beta keto group, you need an ester to be attacked.
It's gonna have to be like a 1, 2, 3 thing. So I drew that. So I know that's what I need.
You need it to be nucleophilic.
Yeah, well, because then that would mean that wouldn't I have to do like, would it be the OME because it's a methyl, or does that not apply yet?
Yeah, but the methoxide, it should be negative.
Yeah.
Methoxide can react with that compound, but then
Oh, we want it to. We want.
But then it might react with
selective,
itself.
So then LDA.
there you go. Or if you want to, just show what LDA and that compound make. Because I don't want these separate. I want this compound with LDA. Or in other words, I want the enolate that LDA makes from that compound.
And then, but I thought LDA was making this.
Maybe it can, but we're focused on this step. You've got a conjugated carbonyl.
Would end up. Okay, so then it would end up. I can't do it. It ends up like this.
Yes, exactly. So either draw the ester and LDA or just draw the enolate.
Okay, and then I need to like draw that. That's what that means.
Wow, the time is really flying.
So it
2
makes
practice problems.
that. Yeah, it's horrible.
Yeah, we need it like so easy.
So LDA makes that,
Try this
but
really
then
really quick.
oh, but then because that's Clayson, isn't it?
Kind of. It's like Claisen-esque.
Oh, that's why we were talking
Or
about
Deichmann-esque.
that. And so then it'll end up like this. Well, or but backwards.
Well, it actually wouldn't end up like this. It would end up more like this.
Oh. Frick, how does that? Oh,
Well-
instead it adds right here. But
Okay, we have to be careful. Oh, that's not the right structure.
Oh, what was it?
I'm gonna change this.
I don't know. Why did you add a phenyl ring? Oh, I see what you're saying. That's not a phenyl ring, though.
Oh.
Or just draw a circle in there and make it a phenyl ring.
Oh. Oh, I was gonna put pH in there. Oh no.
Right, right.
Would this work? Switch this.
DMSO does alkene cleavage. Yeah, so it would break open that ring. Okay, I want to solve one step that I think most of you have gotten. Let me actually check on Indigo first before I give it away.
Sorry, as you're about to. So, did you do this to attach that to get here? But then, is there a way to get this alpha to attack that alkene?
So this alone won't attack this. This as a nucleophile would attack this.
Base, right?
Yeah, and actually the best base would be LDA, so it doesn't react with itself.
Okay.
Or, instead of showing the ester and LDA, we could show just the nucleophile that it makes. But this is great. When this makes a nucleophile, it attacks the beta position.
What did it attack?
When this reacts with a nucleophile,
But that beta's full.
well, it is full. So is this. In fact, you have put the attack here.
On the alpha.
Actually, you've shown it a bit opposite. You've
Well, I
said,
flipped it.
yeah, you said this will attack the ester.
It was easier to view it if I flipped it.
I see. I think I see where you're going with this.
Because then, like, you just need this carbon to attack it there.
Yep.
And change that alkene into like that.
Yeah, so do the Michael addition here.
Is that, would that be, how would you do that? Get this alpha to attack the alkene?
Well, make an enolate attack a beta position. So you just have to turn that into an enolate.
Maybe.
You have to turn that carbon into an enolate. You have to deprotonate that carbon, and then it will attack the beta position.
But that is a beta position.
Yes, it is. A conjugate position. Do you want me to look at something?
No.
Hints? These are the two main syntheses. You will need to do a Michael addition, and you'll need to do a Claisen or Deichmann type reaction where a ketone attacks an ester to leave you with the shared beta position. I thought that it needed to be done in a specific sequence, but Indigo has shown it doesn't need to be done in a specific sequence. You can do it in either. She's very close. So you want hints and not the solution?
No, I want the answer, honestly.
Yes, just the front part.
I'm close to figuring it out. So.
You can leave the room.
Go away.
Throw some earphones or something.
All right. Well, I'll give the first step. The first step is an aldol condensation with acetone, which is the compound we already have. I know this threw some of you off, but you can just say that two of the equivalences will react with themselves. You don't have to explicitly say that, but I did have that bite me in the butt a few semesters ago because there's a multi-step synthesis on the unit test that started much like this. And I did not say two equivalences, but I was anticipating that students would use two equivalences of it to do an aldol condensation. And then students were giving me all sorts of different combinations of things. And so I just changed it. And I said, use two equivalences. Please, there's nothing else that you should be doing here. Aldol condensation. Does this help you figure out some of the positioning into your final product? I think it should. Two methyl groups at a beta position. Two methyl groups at a beta position. So somehow or another, this beta position will need to be attacked by this alpha position, Michael addition. And somehow this alpha position will need to attack this carbon but preserve a ketone, which is similar to Claisen. Claisen has a nucleophile, attack an ester, kick off a leaving group, and keep a carbonyl. I don't think you've mapped your carbons correctly though.
Yeah, I think.
Where does this nucleophile attack?
That. Oh wait, but that's an enolate. Oh wait.
I don't know. I'm so struggling right now.
So here's alpha. Alpha attacked beta. Beta was connected to alpha.
Oh wait.
So I got alpha connected to beta connected to alpha. Yeah?
So this one, wait,
Mm-hmm.
that one attacks. So this guy is this guy.
Sure.
which
It's symmetric in this case, so it doesn't quite matter.
Okay.
This guy attacked this guy, created that bond.
Okay.
Okay, so this guy.
I'm gonna erase this one because it's throwing me off.
Oh, okay.
Or is
Most
he
of it.
beautiful?
Most of it was good,
Okay.
but that's okay. This guy. How do you want to label it? Alpha
This guy
attacks.
attacks this guy.
Good.
Okay.
All right. Now see
Puts
if you
the
can
two over here.
sketch those together.
I'm close.
Okay.
I've got it positioned the way that it needs to go, but I don't know what this is.
Okay, can you draw the product? Once you see the product, you might understand it better.
But,
And this means mapping your carbons.
well, I know this is 1, 2, 3, 4, that's 5, 6.
Okay, let me see it.
But I know some of the double bonds are going to disappear, and I don't know what it is going.
Use the template that we've already used. Nucleophile attacks electrophile. So that's alpha. I know you labeled alpha, beta, alpha over here, but you only labeled alpha, beta, and not alpha.
And, oh, because this is alpha.
Yep.
Oh, no.
Oh, it died. Bummer.
Why
So
don't we just disconnect?
this alpha attacks here.
Because you're talking this one?
Mm-hmm. That's the nucleophile. And that nucleophile attacks the electrophile.
Yeah, it is the nucleophile because this is like the major resonance form, but that's not technically where it attacks from.
Correct.
That's what's throwing me off.
And this will be the template of what you form. Michael addition forms a shared beta dicarbonyl.
This isn't Michael addition though. This
Yes, it is.
Oh,
This
well,
is
no, I'm saying like, it's this step that's gonna be, or is this step supposed to be Michael addition?
this step that you're working on is Michael addition. So you know the template of what your structure should look like. Your structure should look like a shared beta dicarbonyl.
It looks so weird.
Yours looks weird because you got that one long chain in the middle. That's all.
I didn't know how else to draw
It's
it.
okay. You've
Is
got
that
it mapped. It's not wrong. It's just funky looking. Mm-hmm.
Wait, I just did something wrong.
Does
I don't know
this
where I am anymore.
work? I'm trying to decide between keto and meow.
You nailed it.
Yeah?
Yep.
Cool.
The methoxide is necessary because you chose a methyl ester.
Right, because if there was, see, I wrote this
That's it.
down. If that's not there, use meow.
Now I'm going to throw it off and give you
Don't do that.
isopropoxy.
How did you draw it? Does it look prettier than mine?
Yeah. Oh, no. I mean,
I was trying to come up with like how you would get this to connect. Would that work? But then that'd make a pentane, right?
no.
Would that make a pentane?
So 1 attacks 2, 3, 4, 5, 6. 1.
Yeah, okay. So then, would that work though? Those
Absolutely. Actually,
'cause then it would make
yes.
a group,
Exactly.
and that's it, right?
That's it. Nailed it. So do you see how you used Michael addition and like a
So guys, are these all Michael edition, or would like which one's the Robinson?
Robinson is Michael followed by intramolecular aldol.
So these are all Michael edition.
I think Michael addition requires the nucleophile to be an enolate. If it's not an enolate, like if it's an organocuprate, then it's just conjugate addition. Michael didn't get credit for cuprates.
So is Michael edition. Will you look at mine? I think. How would you define?
Yes, I will.
I was just wondering if, I don't really know, is this what's was supposed to go here to make this? Or like what was
This is the one that's
reagent?
not isolated. Yeah, we use this.
This to make that?
Yep.
Okay, I'm really confused on that mechanism, like how that became that.
Yeah.
I don't know.
I'll be honest, when I ask about Robinson annulation questions on the final, it's usually in the form of multiple choice.
Okay.
And it's typically like which intermediates will you see in this mechanism, or what description is correct of the final product,
Okay,
conjugated carbonyl.
okay.
You won't have to do the mechanism for a Robinson annulation. But I think that I didn't do a great job here because the enolate you see here is not the enolate that is immediately formed here. This would depend on interactions between molecules forming the necessary enolate.
Okay.
Yeah. Uh-huh. Ella? So close. You
What did I miss?
had alpha attack beta, but why did this leave? This doesn't leave.
It doesn't leave? Oh.
This is a nucleophile.
Because it has to be kicked off.
It has to be kicked
and
off.
That's where that comes from. Okay.
No.
Oh.
You're adding that.
Well, I know, but I'm saying, and that's why. Oh, and
That's why you
I
need
have
it.
to have it. Yeah,
That's
yeah,
right.
yeah. I was like thinking that, but then
if you wanted to,
so then.
instead of driving the heat and healing.
Oh no. So then it's like that.
Acid workup.
So then it's like that.
Yes.
Okay.
Yes. All right, the solution. There are two possibilities, as Indigo proved, so I'm going to give you two different options. One, and the one that I was anticipating, is do a Michael addition. I've got a conjugated carbonyl. Let's take advantage of conjugated carbonyls and do Michael addition. So introduce a actually, I can't work forward, I have to work backwards, because it's at this point that there's a lot of things I could introduce, but in order to be able to do the last reaction correctly, I need to know what the starting material looks like. This is that Claisen type condensation. So I'm going to have this nucleophile at this position attack an ester at this position. And when that happens, when this ketone attacks this ester, then the ester will kick off its ester linkage, but stay as a carbonyl. Ella, this is exactly the same as yours. It's just flipped upside down. I could have also done an ethyl ester. It does not need to be a methyl ester, but whatever ester I use, that's the type of base I want to use. And then, as always, that base is a catalyst, so it would deprotonate that highly acidic center alpha carbon, which means that I'll need an acid workup. So that is how I form the beta keto carbonyl. I do a Claisen type reaction or a Deichmann type intramolecular reaction. It's not Robinson annulation, because Robinson annulation requires an aldol condensation, not a Claisen condensation, but similar. So I want to take this compound into this compound, and that means that I'm forming a bond to my beta carbon from the alpha carbon of an ester. So I want an ester enolate. And again, I can form an ester enolate by saying, give me this ester with LDA. If I said first, then second, in either direction, then I'm not getting what I need. I want this enolate, so I need LDA with this ester. I would accept either of these. Because if you say this, especially without 1 and 2, you don't have this. You have this. So that is okay. Those are synonymous. What Indigo showed was that we can take the alpha position of our conjugated carbonyl and we can use it to form a nucleophile with an ester and do that Claisen type condensation. And give us the shared beta dicarbonyl first. And now we can do an intramolecular Michael addition. I need this alpha carbon to attack this beta position. And if we're working through this properly, this would actually need an acid workup. I don't know if I caught that on yours. But anytime we make that beta keto carbonyl in basic conditions. We'll need to do an acid workup with it. This creates a nucleophile here that then attacks at the beta position and leaves me with the product that I want. I think that I would, if I were going to try this in the lab, I think I would still try the route in green. One thing that I'm not sure, because textbooks don't always hit on everything that's plausible, I'm not sure how the acidity of these hydrogens compares to the acidity of this hydrogen. These hydrogens down here after the beta position, if they get deprotonated, they can be in resonance with the oxygen. Technically, more resonance forms, although the additional resonance forms places the negative charge on a carbon, so it's not like it's a great resonance form. We could argue that the induction from the oxygen being closer to these alpha hydrogens makes them more acidic, but I don't know. And textbooks don't always say that because that's not how they teach their reactions. But I agree, very plausible. Max?
The second step, does it need an acid workup or does it not?
You're right, it does. After we do this nucleophilic attack, the oxygen holds the negative charge and needs an aqueous workup.
Yeah, I was talking about the green one too. The second step on the green one, like with the ester and the enol.
Good point. Yep,
Okay, they're both equal.
thank you. Yeah, the Michael addition leaves you with a negative charge. So the Michael addition requires an aqueous workup. Good call. Indigo. Oh yeah, the second one, which was so much easier, I forgot. Okay, the second one I recommend doing in this, what is the second one? What functional group do you see formed there in the first step? A conjugated carbonyl, aldol condensation. So I recommend doing an intramolecular aldol condensation. 1 attacks 2, 3, 4, 5, 6. So this requires just NaOH and pops out a water molecule. Then it would be best to do conjugate addition. Whoops. And the cuprate that I want is a vinyl cuprate. I want my alkene attached to my copper, an aqueous workup. This takes care of my conjugated carbonyl and gives me that new alkene. Then, if I introduce this enolate, the next reaction is just another aldol condensation. It leaves me with a new conjugated carbonyl. And then I can do another Michael addition and another aldol condensation and another Michael addition and another and that would maybe require some extra base to see it run through. Another way that you can report this, again, is you can say, I want the ketone with LDA. Those are saying the same thing. You could maybe swap the aldol condensation and the Michael addition step, but if you form another conjugated carbonyl and then try to do conjugate addition, which conjugated position will it attack? That would be the downfall.
Does that last step require an aqueous workup as well? Or no?
Yeah. To be honest, I think it requires water for sure, but not an aqueous workup. So this would be good enough. Or you could add water underneath it. Or you could add hydroxide underneath it.
Yeah, because water is a byproduct on the previous step.
Yeah. Great work, guys. Thank you for your time. Come with questions Tuesday and Thursday. And good luck on your unit test this weekend.
Can I ask you like how part of that works, or like where it attacks?
Yeah?
Like